Alkanes का part 3 Orientation of halogenation. It has been observed that sometimes a compound can form different products on reaction with the same reagent. This means that the compound has more than one reactive sites where the attack by the given reagent can take place. The process of determining the particular site or sites in a molecules where the reaction is most likely to occur is known as orientation. It involves the examination of factors which can influence the relative rates of competing reactions. For the present, let us consider the orientation of halogenation of alkanes. It has been pointed out earlier that the halogenation of higher alkanes can lead to the formation of two or more isomeric products. For instance, the chlorination of propane at room temperature produces a mixture of N-propyl chloride and isopropyl chloride in the ratio 45:55. The rate controlling step for the two competing reactions involves the formation of N-propyl and isopropyl radicals by the abstraction of a primary or a secondary hydrogen of propane as shown below. Naturally, the relative quantities of the two halides produced would depend upon the relative rates at which N-propyl and isopropyl radicals are formed. Let us examine the various factors including that is collision frequency, probability factor, energy factor, which can influence the rate of formation of these radicals. Collision frequency. As far as the collision frequency is concerned, it must be the same for the two reactions since the same particles, that is, propane molecules and chlorine atoms, are involved in each case. Probability factor. The probability factor concerns the orientation of propane molecules at the time of attack by chlorine atoms. For the formation of N-propyl radicals, the propane molecules must be so orientated at the same time of collision that the chlorine atoms strike against a primary hydrogen, which get abstracted. Similarly, the formation of isopropyl radical would require the propane molecules gets to be so oriented that the chlorine atom collides against a secondary hydrogen which gets abstracted. Now, there are 6 primary and 2 secondary hydrogens in each molecule of propane. Therefore, the probability factor should favor in the formation of N-propyl radicals by the abstraction of hydrogen in the ratio 6:2 or 3:1. Energy factor. It is evident that the combined effect of collision frequency and probability factor would require the formation of N-propyl chlorine and isopropyl chlorine in the ratio 3:1. However, the actual ratio of product formed is 45:55 or roughly 1:1. The proportion of isopropyl chlorine chloride thus about 3 times the expected value. This means that about 3 times as many collisions with secondary hydrogens are effective as compared to collisions with primary hydrogen. This is quite in keeping the influence of energy factors. Since isopropyl radical, a secondary radical is more stable than unpropyl radical, a primary radicals, the transition state leading to the formation of a formal radical must also be more stable and therefore have lesser energy of activation. In another word, E activation for the abstraction of secondary hydrogen and consequent formation of isopropyl radical is lesser than that for the abstraction of primary hydrogen and formation of N-propyl radical. That is why the formation of isopropyl chloride take place preferentially. Similar investigation involving chlorination of other alkanes indicates that the relative proportion of various isomeric chlorination products are related to the E activation for the abstraction of different classes of hydrogen atom and the formation of corresponding alkyl radicals. In general, the rate of abstraction of hydrogen atom and formation of corresponding free radical is found to follow the order tertiary, secondary, primary. In fact, during chlorination at room temperature, the relative values of rate of abstractions for tertiary, secondary, and primary hydrogen have been found to be 5:3.8:1 per hydrogen. It is interesting to note that relative values of rate of abstraction of hydrogen also depend upon the nature of halogen used. Thus, the relative values of rate of abstraction of tertiary, secondary, and primary hydrogen in bromination have been found to be 1600 ratio 82 ratio 1. These are clearly quite different from the values in case of chlorination. Knowing the probability factor and relative values of rate of abstraction of different hydrogens, or in other words, their relative reactivities, it is possible to predict the ratio of isomeric halogenation product obtained from a given alkane. For example, in the chlorination of N-butane, the relative amount of monochloro product formed may be calculated as follows: N-butyl chloride by secondary butyl chloride is equal to number of primary hydrogens upon number of secondary hydrogens into reactivity of primary hydrogen into reactivity of secondary hydrogen. The expected ratio of two products calculating above is equivalent to 28% of N-butyl chloride and 72% of secondary butyl chloride. The actual percentage is found to be same. Reactivity and selectivity. Chlorination versus bromination. It has been studied earlier that in the halogenation reactions of alkanes, chlorine is more reactive than bromine. It has also been discussed that in case of alkanes containing different type of hydrogen atoms, the ease of abstractions or reactivity of different type of hydrogen follows the order tertiary, secondary, primary, irrespective of the nature of halogen taking part in the reaction. But now we consider a very interesting observation with the help of a simple example. When propane is subjected to chlorination, N-propyl chloride and isopropyl chloride are formed in the ratio 45:55. But when propane undergoes bromination, N-propyl bromide and isopropyl bromide are formed in the ratio 4:96. Keeping in view the number of primary and secondary hydrogen, it is clear the secondary hydrogen of propane are more reactive than primary hydrogen in both the cases. But there is much more selective abstraction of tertiary, secondary, and primary hydrogens of alkanes in chlorination are 5:3.8:1, while in bromination the relative rates are 1600:82:1. This means that bromine is less reactive but more selective in its reaction with different type of hydrogen. On the other hand, chlorine is more reactive but less selective. This is in accordance with the reactivity selectivity principle, according to which if the attacking species is more reactive, it will be less selective, while a less reactive species is more selective. To understand the above principle, let us consider the transition state involved in the rate controlling step, that is attack of halogen free radical on alkanes of chlorination and bromination of alkanes. The reaction of highly reactive chlorine atom with alkane has very low E activation, and therefore the transition site is reached quite early when the alkyl radical character has just started developing. Therefore, the stability of alkyl radical ultimately formed does not have much effect on the ease of occurrence of the reaction. RH plus chlorine radical gives transition state of RHCl gives R radical plus HCl. In case of much less reactive bromine atom, the above state involves high E activation. As such, transition state is reached very late when sufficient alkyl radical character has already developed. Therefore, the transition state resembles ultimately formed free radical instability and ease of formation. In other words, bromine atom will attack the tertiary hydrogen relatively much more easily than secondary, which in turn would be attacked more easily than primary hydrogen. Hence, as compared with more reactive chlorine, there will be much more selectivity in the reaction with less reactive bromine. Interconvergence of alkanes. During the study of organic chemistry, we are often required to prepare one organic compound from another. Sometimes this may involve preparation of a higher member of a class of compounds from a lower member or vice versa. We now illustrate the procedure followed by considering the interconversions of alkanes. Preparing a higher alkanes from a lower member. This involves the following steps: chlorination or bromination of given alkane into monochlorine derivative. Second, Wood's reaction or Corey-House reaction of the monochloride derivative obtained with a suitable alkyl halide or lithium dialkyl copper as required. Preparing a lower alkane from a higher one. This involves the following steps: conversion of given alkane into alkyl halide, hydrolysis of alkyl halide obtained to get an alcohol, oxidation of alcohol formed into carboxylic acid, decarboxylation of acid via its sodium salt to form the alkanes. Thank you.